Section 14.1, trees and minimum spanning trees. A connected graph is a graph in which there is at least one path between each pair of vertices. A tree is a connected graph in which there are no circuits. Example 1. The following graphs are trees. It's connected, but there are no circuits. Our second example of a tree. You could think of the middle as the tree trunk and the ones going out as the branches. Third example of a tree. Again, the trunk and the branches. Just the tree trunk and just the branches. Example 2. The following graphs are not trees. That graph is not a tree because it is not connected. Not connected. It is not a tree because there are circuits. And again, not a tree because of the triangle part that is the circuit. The unique path property of trees says that in a tree, there is always exactly one path from each vertex in the graph to any other vertex in the graph. Example 3. Joe has an old underground irrigation system in his garden with connections at the faucet F, outlets A through E in the garden, and existing underground pipes as shown in the garden. Joe wants to renovate the system, keeping only some of the pipes. Water must be able to flow to each of the original outlets, and the graph of the irrigation system must be a tree. Design an irrigation system that meets Joe's objectives. So we're going to start at the faucet. Looking at that irrigation system that currently exists, there are plenty of places for leaks to happen or pipes to burst and to have problems. So we'll start at the faucet. And we'll go to point E. Go back to our faucet. And we can go to A. From A to B to C. And from A we can also go to D. There is an irrigation system that meets Joe's objectives. Many less opportunities for pipe problems. The number of edges in a tree with n vertices is n minus 1. Given a graph with n vertices, if the number of edges is n minus 1, then the graph is a tree. If the graph is a tree, then the number of edges is n minus 1. So if it's a tree, it has n vertices, n minus 1 edges. Example 4. A chemist has synthesized a new chemical compound. She knows from her analysis that a molecule of the compound contains 54 atoms and has a tree-like structure. How many chemical bonds does the molecule have? There are 54 atoms, so there are 54 vertices. We know it's a tree, so our number of vertices n equals 54. Our number of edges will be n minus 1, 53. So there are 53 chemical bonds. Example 5. If a tree has 15 vertices, what is the greatest number of vertices of degree 5 this tree can have? The sum of the degrees, recall from previous section, the sum of the degrees is 2 times the number of edges. If there are 15 vertices, we know there are 14 edges. So we'll do 2 times 14 and see we have 28 degrees. If there are 4 vertices of degree 5, that totals 20 degrees. That means there are 11 vertices left, but 8 degrees left. So that is not a possible option. If there are 3 vertices of degree 5, that totals 15 degrees. 3 vertices of degree 5 leaves us with 12 vertices and 13 degrees. We used 15 of the 28. 12 vertices, 13 degrees. Yes, that is possible. So the greatest number of vertices of degree 5 is 3. A spanning tree for a graph is the subgraph that includes every vertex of the original graph and is a tree. Example 6 is find 2 different spanning trees for the graph below. So we want to keep all of the vertices but eliminate edges to make it a tree. Just drawing the vertices, A, B, E, E, C, and D, F, H, and G. Okay, so let's keep A, B, and E connected. We'll take away that edge from C to D, stay connected to F, and take away that edge from F to H. Another option, go ahead and draw your vertices. Whoops. We'll just keep it there. I was already thinking about how I was going to connect things, change it up. I'll connect A to B, B to E, E to D, D to C, D to F, and I'll connect F to H and F to G. There are many different spanning trees that could be created. Counting spanning trees. Assume that no 2 circuits in the graph share a common edge. If the graph has n disjoint circuits, a spanning tree is constructed by removing one edge from each circuit. To construct a spanning tree, perform n tasks. Remove an edge from the first circuit, remove an edge from the second circuit, etc., etc., until you have taken an edge away from each circuit, which is what we did in the previous example. A minimum spanning tree for a weighted graph is a spanning tree that has minimum total weight. Kruskal's algorithm helps us find a minimum spanning tree in a connected weighted graph. Choose any edge of minimum weight to be the first edge. Start with the minimum weight. Choose any edge of minimum weight from among the edges not selected. They don't need to be connected. Continue choosing edges of minimum weight from among the edges not yet selected, except do not select any edge that creates a circuit. Repeat step 3 until the subgraph connects all vertices of the original graph. Here's our graph. And example 7. There are 6 villages in a certain rural district. At present, all roads are gravel, and there isn't enough funding to pave them all. But there is an urgent need to pave enough of them so that emergency vehicles can travel easily from one village to another. Vertices in the graph below represent the villages, and the edges represent the existing gravel roads between them. Estimated costs for paving these roads in millions of dollars are shown. The district council wants to pave just enough roads so that emergency vehicles can travel from one village to another on paved roads, and they wish to do so at the lowest possible cost. Use Kruskal's algorithm to find an optimum strategy. So we'll start with our minimum weight, which is E to D, being 1. I'm going to put the other vertices in because we know what we want to connect. And over here we have C. So E to D is our minimum weight. Our next minimum weight is from F to B at 1.5. Go ahead and connect those. Our next minimum weight is from D to C at 3. Our next minimum weight is 4 from D to B. Oops, I wanted to put a 4. And we still need to connect A. That is the only vertice we haven't connected yet. So if we went from E to A, that would be 7. If we went from A to F, that would be 10. And if we went from A to B, that would be 7.5. To keep it at the minimum, go from A to E at 7. Lowest possible cost, add it up, 7 plus 1 plus 3 plus 4 plus 1.5. Our lowest possible minimum cost is $16.5 million. That's section 14.4, trees and minimum spanning trees.